All right, are you guys excited about reviewing chemistry? I hope so. I'm hoping that a lot of this will be familiar and there's skills that we practice in one form or the other. So I hope it comes back to you, but don't underestimate this. Like I said, last year's final exam, surprisingly, kids didn't do so well on the chemistry section. Now, starting off, first of all, a couple things. It says what to know for test two. Remember, test one was just the elements test, memorizing part of the periodic table. So this was actually the first test on the material. So it's kind of the unit one material. Now, I didn't give you like a review sheet for this as far as just a bunch of problems, because again, you have a bunch of problems that you can redo. So remember in the spring, I started giving you sheets like this that kind of reminded you kind of a checklist of things that you should know. So what I'm gonna do is, I don't have it really structured very well, so excuse me if this is a little scattershot, but I think I'll kind of go over this review sheet and then maybe I'll go over it first and kind of just say things generically. And then I have all the problem sets for this unit down below. And I just kind of selected some problems to do. So anyways, let's just go ahead and get started. Not much else to say. All right, so getting to the first topic we did, parts of the atom. So I guess I can't zoom in because you need to see the whole sentence. And you have this sheet, or I'll be sending it to you soon if you don't have it. So know parts of the atom. Maybe I'll do a highlight here. And again, this should be pretty obvious. You know, you've been doing this. That maybe I'll go up here and just remind you. I'll get a black pen here. We have, again, not to scale because the nucleus is incredibly tiny compared to the size of the atom, meaning the extent of the electrons. So here I did red protons and blue neutrons and then green electrons. So yeah, that's a proton. So that's one part. We have a neutron. So those collectively are called nucleons. So if you run across that term in the final, a nucleon is just a generic word for a proton or a neutron, the things, quote unquote, inside the nucleus. They have about the same mass. They're about 1 Dalton each. Slightly different, but basically 1 Dalton each. And then the electrons are really small. I'm trying to remember the exact mass. I think it's like 1/1836 of a Dalton or something like that, but it's basically negligible. So if we were totaling the mass of everything in this atom, you just kind of ignore the electrons. So how many nucleons does this atom have? 7, right? 4 neutrons, 3 protons. So what's the approximate mass of this nuclide, this atom here? It would be about 7 Daltons, right? So that's how you get the mass, is you just figure out how many nucleons it has. Now, how would we write the symbol for that? Well, if this is 3 protons, you look in the periodic table and you'd see the one with 3 protons, which is the bigger number there, not bigger number, the number at the top, I shouldn't say bigger number, is the number of protons. That's the atomic number. So that's element 3, which is lithium. So that is a model of a lithium atom. And just to review how you write the numbers, is at the bottom left, we write how many protons it has. And we call that the atomic number. So these are terms you should know. They could come up. And that's just the number of protons. Then at the top left, you write a 7 for this atom. That represents what we call the mass number. And that's the total number of nucleons. Not the number of neutrons, but the neutrons plus the protons. So this would be called lithium-7. The 7 meaning that it has 7 nucleons, therefore a mass of about 7 Daltons. Now what if I did this? What if I took my eraser and I erased one of the electrons? So that lithium atom is no longer neutral. A neutral atom has the same number of protons as electrons, but now I got rid of an electron, so it's no longer neutral. So how would we write the symbol for that? Well, on the top right, we put the electric charge, not how many electrons it loses or gains, but what the overall charge is now. So since it has 3 protons, after all, it's lithium, but only 2 negative electrons, the overall charge is just +1. And if it's a 1, you just leave off the 1. So that would be lithium-7 +1. That's the charge. So again, don't think plus means it's gained electrons. it's backwards to kind of what some people think. Plus means it's lost an electron, and so that's why it's positively charged. Okay, I won't spend so much time reviewing that, but I thought that might be a little review because a lot of that information will be in the problems that follow. So the terms, atomic number, we just covered that, how many protons, mass number, how many nucleons. The fact that the number of protons is what gives each element its individual identity. So the fact that something has 3 protons means it's lithium, or something that's lithium means it has 3 protons. So that's kind of what gives each atom its own special flavor, is how many protons it has. I already kind of covered that the mass is pretty much due to the nucleons. Then we'll cover isotopes. So the idea, when I do some problems there, an isotope has to be, or isotopes of each other, have to be the same element. You can't have lithium and beryllium be isotopes. Those are 2 different elements. So isotopes are 2 versions of an element, therefore having the same number of protons, that just have a different number of neutrons, and therefore they'd have a different mass number, and therefore a different mass. So for example, this atom that I just drew up there is lithium, but it has 4 neutrons, and so therefore it has a mass number of 7. It's about 7 Daltons. But what if I did a version of lithium that now has 5 neutrons? Well, that would no longer be lithium 7, that would be lithium 8. I'm not worrying about the charge there. So that would be about 8 Daltons because it has 8 protons and neutrons. So those 2 are isotopes of each other. Same element, but just a different number of neutrons, and therefore different mass numbers and different masses. Okay, even if that were neutral, so that was just 0 here, it's just a neutral atom, those are still isotopes of each other. The charge doesn't affect whether they're isotopes or not. Who cares how many electrons it has? The only thing that's important is that it's the same element, but with a different number of neutrons. Okay, we'll see some problems like that, pretty easy, as I move down to the problems. The mass listed in the periodic table is the weighted average. And I'll tell you a little bit later the type of problem I may or may not ask. One thing I'll just give away now is, since we didn't really practice it, it's not that important. I'm not going to have you calculate the average atomic mass or calculate the percentage of one or the other as you do these, but I might show you some other problems we're doing. So for example, the classic example is over here, chlorine 35.5. So there's no such atom of chlorine that's 35.5. It's just that there are different isotopes of chlorine, and taking into account the natural abundances of all the naturally occurring isotopes of chlorine, the average turns out to be 35.5. Not a big deal, but that's what I meant by that bullet. Okay, next bullet. What I might do is, well, I'll just go over everything. The mass, I just went over that one. That's the weighted average. Neutral atoms have the same number of protons as electrons. I mentioned that. An atom forms an ion by losing or gaining electrons. So yeah, something that is going to form an ion isn't forming an ion because it's losing protons or gaining protons. It's the electrons that are being lost or gained. And then here are 2 terms you probably will need to know. I'm not positive, but just be ready. Remember that a cation is a positive ion and an anion is a negative ion. So write those down if you don't think you'll remember. I'll show you what I mean by these puzzle problems once we get to the problems. It's like where I give you the number of electrons and the neutrons and ask you for which element it is, things like that. So don't worry about that. I'll show you what I mean by that when I get down to the problems. Similarly for this one, know how to interpret this nuclear symbol or write the symbol. So what I mean by that, and again, I'll show you problems, I'm just kind of going through this list kind of quickly, is if I gave you something like this, if I asked you how many neutrons, protons, and electrons it has, you can tell me. Or vice versa, if I tell you how many neutrons, protons, and electrons it has, you could write the symbol. Okay, hopefully that doesn't feel like I'm going fast, because again, I'm just going through the list, and then I'm going to go down to the problems in a bit. And yeah, start making a list, pause this video if there are things you want to write down, like for example, writing down what a cation and anion is. Okay, periodic table. So up here, maybe I'll just review it, but let me just quickly look at this. Know the difference between metals, nonmetals, and metalloids, not just in where they're located in the periodic table, but in terms of their properties, okay? So likely I'm going to ask something about the properties. It's kind of an important idea of chemistry. Know how to name the different regions. And again, I'm going to go up to the top of this document and review all this. The rows are called the periods. The columns are called the groups or families. And the idea is the elements within a particular family, like a particular column, kind of behave alike. Not exactly, but they have similarities. And then know the names of certain columns. You should be used to those. And know that hydrogen is not an alkali metal, even though it's in that column. And then importantly, for many topics this semester, know what the likely charges are. Write them down. I'll probably say this 3 or 4 more times during this video. You write those down so you don't forget. And then I'm sure I'm going to cover that when I get to the problems below. All right, so let's just review a few things here. And you might not need it because, again, we practice this so much. So let's name some things. I guess I'll go ahead and use a pen. So again, let's do the metals and non-metals and stuff. So all the kind of white background ones we consider pretty much metals. Those are the metals. And then the dark background ones are the non-metals, including over here, hydrogen. So those are the I'll just put non-M. And those lightly shaded ones along the zigzag line are going to be the metalloids. I don't ask you much about that because it's just they don't have unique properties. They're kind of in between metals and non-metals. So know how to identify them, but also know the general properties of these. So mainly, I kind of know these facts. Metals, maybe I'll write it down here so you can see it a little bit better. Kind of a key idea of metals is they prefer to form positive ions, cations. So I'll say form positive ions, cations. And other properties that you should know is that they tend to be shiny metals. Well, yeah, shiny solids, I'll say. So these metals typically are all solids. There's only one at room temperature that's not a solid, and that's mercury. And they conduct electricity and heat well. And another thing about these metals is not all of them, but if you heat them a little bit, they tend to be like pliable or malleable or things like that, ductile. Pliable means that you can bend them. Malleable means that you can I think it's hammer them into thinner sheets, and ductile means you could draw them into wire. So, warm them up and they might be able to do that. Okay, and then just the non-metals, the general properties you're looking for, and write these down if you think you'll forget. They form anions, negative ions. That's what they like to do. They tend to be dull solids, not shiny solids, or gases. Oh, there's also one liquid, bromine. They are insulators, I'll just say that. So they're not good conductors. They insulate both heat and electricity. And these tend to be brittle if they're solids. Okay, so I'm not going to say much more about that. Just know metals, where they are in the periodic table, and kind of know their general properties so you can distinguish them. And again, metalloids are kind of in between. All right, let me quickly erase this page. I think it's this button right here. Quick page, okay. And then just review some other things. So the names of the columns, I wonder if I can make this pen a little bit thicker. Go through there. Okay. So these are the alkali metals. These are the alkaline earth metals. Let's put M. We don't give names for those. We'll just call them group 3, 4, 5, whatever. Same thing for group 13 and group 14. Secretly, I'm not going to ask you this, but I'll just, if you want to have a little trivia knowledge, a nitrogen's column is called the nicogens. It's spelled P-N-I-C-O-G-E-N-S, but I won't ask you that. And similarly, I'm not going to ask you oxygen's column. We just call it the oxygen family, or group 16. But they're called the chalcogens, kind of spelled chalcogens. But you should know these are the halogens. And these are the noble gases. Okay. And remember that the rows are called the periods, and the columns are called the groups or families. So I'm not trying to be quick. I'm not trying to be neat here. I'm just trying to be quick. You can always pause the video and write these down in your notes if you want. Special names, those are the lanthanides, or as you see there, lanthanoids. And then these are the actinoids or actinides. What else? The first 2 columns and the last 6 columns, those are the main group elements. Right? So that's what we typically do in introductory chemistry courses. We kind of just focus on those. And then these are called the transition elements or the transition metals. I usually call them transition metals. And technically these are called the inner transition metals, but I never really use that term. So I think that's it, except for one big thing that you should know. Maybe I'll do it in green. Yes, please write down, if you don't have it absolutely memorized, the likely charges of these elements when they form ions. So remember, by the way, I forgot to say that, but hydrogen is not an alkali metal. So the alkali metals like to form +1, +2. A boron's family, kind of +3. Carbon and nitrogen's family, they don't really form ions that well. But let's start from the right. The noble gases don't like to form ions, I'll say 0. The halogens form -1. Oxygen's family, kind of at least down to around here-ish, will form -2. And then if I were to guess what nitrogen did, I'd say -3, but I typically don't worry about that too much. Okay, so that's pretty much a good review of everything for periodic table. Now temperature, go back to my smaller pen, there we go. Temperature, I might ask you to convert between Celsius and Kelvin. I kind of feel guilty because I didn't tell you to write that down. I'm not sure if I told you to write it down. So if I just don't think it's worth it. So I'm going to ask you, but you should just write it down just in case. So the formula you want to use, I always just say, you know that they're 273 different, and the temperature in Kelvin is always the bigger number. But if you want like a little formula, the temperature in Kelvin is just the temperature in degrees Celsius plus 273. And technically you don't say degrees Kelvin, you just say Kelvin, or more properly Kelvins. But anyways, that's how you get from one to the other. And I don't think I'm going to ask you this idea here, but temperature is just the word we use to describe the average kinetic energy of the particles moving around or vibrating. And that's about it. For future courses, understand that the size of 1 Kelvin is the same as the size of 1 degree Celsius. They have a different 0 starting points, but if you change the temperature by 5 degrees Celsius, you're also changing the temperature by 5 kelvins. And then we'll see maybe or maybe not questions you have to answer. For the test we did, you had to, but again, the final, I can't ask many questions on this unit. So I'll probably skip this pretty quickly. Well, maybe I'll just go over it a little bit. Know the difference between solids, liquids, and gases. I'm sure I'm going to give 1 or maybe 2 questions about this section. So briefly speaking, again, I'm trying to hurry a little bit, but we'll do some questions later, is they differ mainly by their spacing from each other, if they're crammed together or far apart, and their movements, whether they're free to move or have restricted movements. So as I'm saying here, solids and liquids are crammed together, which will explain why they're incompressible. I can't squeeze them any closer. I don't think that liquid particles are farther apart than solid particles. Really, it's not true. If it's true, it's negligible, really. But gases, their particles are really far apart, so they are compressible because there's empty space between them. Solids and liquids differ because they don't differ in spacing. They differ by their freedom of movement. So solids, remember, just are kind of stuck in place. They're just jiggling back and forth. But liquid particles have some freedom of movements, and so they can kind of wander around and take the shape of a container. But gas particles are completely free to move around. There's lots of empty space to move. So that could explain diffusion. Remember, diffusion is how one material moves through another. So gases diffusing through each other, or two liquids diffusing into each other. Solids don't diffuse because their particles are stuck in place. They can't wander into another material. Gases diffuse really easily because they have such freedom of movement that they can just, one gas can diffuse into another really easily. And liquids can diffuse slowly because like if you put a blue liquid on top of a green liquid or yellow liquid, wait a while and they become green because there is some freedom of movement. Probably not going to ask you too much detail about that. It's just going to be some, if I do ask one, something about the difference in the models, and maybe something like a clue about which state it is, solid, liquid, or gas, depending on like those properties, whether they're incompressible or they can diffuse or whatever. maybe I'll ask this. Again, we'll see how much space I have to ask questions. Know the names for those changes in state. Write them down. People miss those on the test and quiz. Please write those down just in case I do ask it. I can't promise I will, but just be ready to name those. I want to take the time to say it. You can read it right there or pause the video and write them on your cheat sheet. Probably not a big deal, but yeah, vaporization just means a liquid turning into a gas. So it's sometimes I accept that instead of boiling or something. I'm probably not going to ask you that, but that's just the idea that the boiling point of a substance is the same as its condensation point. The melting point's the same as its freezing point. And again, we'll get to some sample questions below. All right, so moles. We haven't done that in a while. I kind of partly dropped the ball there, but it just wasn't relevant for much of the stuff we were doing in the second half of the semester. So remember, I will give you this number if you have to use it, but go ahead and write it down anyways. That a mole is just a quantity. Just like a dozen is 12, a mole is just 6.02 times 10 to the 23rd. So it's just a convenient number, as we'll talk about in a moment, that we use in chemistry. So actually be able to convert from moles to what I call actual number, or vice versa, the actual number to moles. And all you do is either multiply or divide whatever you're starting with by 6.02 times 10 to the 23rd. So for example, and I'll do a couple of problems on the homework below, if you have 3 moles of carbon atoms, well, how many particles is each 1 mole of carbon? 6.02 times 10 to the 23rd. So what do you think I do? Divide 3 by 6.02 times 10 to the 23rd, or multiply? Well, yeah, multiply. So if we multiply 3 times Avogadro's number, you get that. So make sure you can do scientific notation on your calculator. Use the second EE button. But what if I told you you actually have that many atoms? Well, what do you do to that? Well, we're not going to multiply by Avogadro's number. We're going to divide. Because doesn't that look like about half of what Avogadro's number is? Yeah. So we're going to divide 3.01 times 10 to the 23rd by Avogadro's number, and you get 0.5 moles. So we'll go over some of those just to practice. But here's the cool thing about this, is why they chose Avogadro's number is it's the perfect number of atoms that if you had that number of atoms, the mass of that collection of atoms is the same number, but in grams, as the mass of one of those atoms are in Daltons. I know that's a big mouthful, and I'm not sure if you got it, but I think you understood it earlier. So the big idea is, if we looked in the periodic table and we see, for example, that carbon says 12 for it in the periodic table, that means one atom of carbon has a mass of what? 12 Daltons. But if I had 1 mole of carbon atoms, meaning 6.02 times 10 to the 23rd atoms of carbon, what is the mass of 1 mole of carbon? 12 grams. So that's what I mean. It's the same number, 12, but when you have one single atom of that atom, it's 12 Daltons. If you have a mole of those carbon atoms, it's 12 grams. And that's why it's just not a particularly friendly number there, but it's just what was needed for that fact to be true. Okay, we'll see some practice problems like that too. So then we learned this term molar mass, which unsurprisingly just means the mass per mole. And we use the unit grams per mole for that. So going back to my carbon example, if you see in the periodic table that it says carbon is 12, then carbon has a molar mass of 12 grams per mole. That's how you pronounce it. And we'll look at some problems in the below. And then here's another important skill, which you'll be doing constantly in 10th grade, converting between moles and mass. Now, what I just did here, I was converting between moles and just the regular number that doesn't involve moles. But here's how we go from a number, moles, to mass. And we'll do some practice problems below. But you use the molar mass as a conversion factor. So if carbon has a molar mass of 12 grams per mole, which we see in the periodic table, we just write the molar mass as 12 grams over 1 mole. But notice we put 1 mole on the denominator, so it'll cancel the 3 moles we're starting with. So 3 moles of carbon have a mass of 36 grams. But what if I give you grams and you want to know how many moles you have? Well, let's say that I have 20, I'm doing this problem above here. I have 28 grams of helium. Well, here's my 28 grams, but if you look in the periodic table, kind of messy here, you see that helium is 4. So it's 4 grams per mole. So there's my molar mass of helium, 4 grams per mole. But notice I'm putting grams in the denominator so that it'll cancel and I'm left with 7 moles. Now, when I do the problems below, I'll probably remind you again, but write this down on your cheat sheet if you're not an expert at it. And so if I give you, when I give you, I should say, notice I said when, not if, I give you a problem where you're converting between grams and moles, you can look at your cheat sheet and it'll remind you how you set that up. You can even write little notes that say, converting from grams to moles or whatever for this one here. And it's just the same thing. You'll just have a different number here, and that will probably be a different number if it's a different element or compound. Okay. So make sure you know how to do that. There will be a problem doing that, unless for some reason I'm brain dead and I forget to do it. All right, radioactivity. What I might do is not give you a little mini lesson here. I want to move on to the problems soon. And the problems are pretty much what I'm going to explain anyways. So I'll probably save that, but maybe just highlighting some ideas here without, actually doing the problems. Know the terms involving radioactivity. We'll go over that. Just know that the strong force is that force between protons and neutrons that hold it together, the nucleus together. The electrons do not experience the strong force. And just a reminder, a lot of the things I'm saying won't be on the final. I don't have that many questions I can ask. So don't get mad if you're learning something and it's not on the final. What else? I talked about how neutrons are kind of important to keep the nucleus stable. I'm not going to ask that. But then here's the thing that I think you got good at, but we'll practice when I do the problems below. If I give you a certain nuclide, a certain atom with a number of protons and neutrons, you should be able to make a good guess whether it's going to be stable or unstable based on the ratio of neutrons to protons. And I'll just review that once I get to the problems below. Okay? And I think that's right here. Yeah, so I'm not sure why I did that as a separate bullet. And then related to radioactivity is doing nuclear decay equations. And again, I'll kind of save that, but instead of re-explaining it here, I'll explain it when I'm doing the problems below. But you should be able to do questions that involving, well, these are like fusion and fission, but you should do similar problems where you're filling in blanks or whatever. Well, not that you're filling them in, it's a multiple choice, but identifying what should be in the blanks for alpha decay, beta decay, and both types, and gamma decay, as well as for fusion and fission. So I'll kind of review all this stuff that's written right here about the difference between those, okay? I'm probably not going to ask you anything about, which is more penetrating, I'm guessing, but I'll mention it later anyways. And then half-life, again, I'll save to the problems because there's not a lot of explanation there. Well, I'll just explain it really quickly here. There are equations you can use, but for our introductory course, this is kind of the table we're going to use. So spoiler alert, of course, I'm going to ask you something about half-life or a couple of questions. So write that down in your cheat sheet. Okay, don't forget that. And then I did mention carbon dating, which is really just going to be a question involving half-life. And then miscellaneous things before we get to our problems here is, no, I won't ask about quarks. I won't ask about that. Yeah, so forget that. I'm not going to ask you. And I'm not going to ask you about E equals MC squared, so you can ignore that. All right, let's hit some problems. I went through earlier and just highlighted some to draw my attention to maybe go over. And again, pause the video if I'm going fast and let it sink in before you go to the next thing that I go over. So really quickly, again, I'm not going to ask many questions about these things on this page until I get to, like this. That's my puzzle problem that I mentioned earlier. So just to see if you're paying attention, let's do one. Feel free to pause again if you want to ever answer them before I answer them. I'll always give a little pause before I start answering it. So they're positively charged and have a mass of about 1 Dalton. That's a proton. I'll just save time by not writing it. They're neutral, have a mass about 1 Dalton. Neutron. A generic term used for a proton or a neutron. A nucleon. I'll go ahead and write that just so you know what I'm saying. They're negatively charged and weigh about a 2,000th of a Dalton. That's the electron. The tiny part of the atom that contains all the positive charge and nearly all the mass of the atom, that's the nucleus. Okay. This is like a simple kind of puzzle problem number 2. An atom has 8 protons and 10 neutrons. How many nucleons? It's not really a puzzle problem at all. 18, sorry, it's not. What would be the mass of that atom? Well, about 18 Daltons. All right, we'll skip those. I mean, it's probably not that important. Do know these terms. Again, I don't think I'm going to ask a separate question about cations and anions, but it might come up in the context of a bigger problem. So a negatively charged ion is called an anion, and a positively charged ion is called a cation. And then I highlighted these. Again, go over all the questions when you're studying, but I'm just going to highlight some of these. So here's this kind of that puzzle problem, not a particularly hard one here. An ion has a charge of -2, and has 36 electrons. How many protons does it have? Well, it must have 34 protons, because by having 36 electrons and 34 protons, it has 2 more electrons than it does protons, and because electrons are charged -1, that gives it the -2 charge. Okay, I probably won't ask one, quote unquote, this easy, but I will ask something along the line here. An ion has 26 protons and a charge of +3. How many electrons does it have? It must have 23 electrons. By having 3 extra protons, that gives it the charge of +3. Okay, I think that's all I asked for that one. Let's do 50. And remember, I'll have sent you all these problems and answer keys. The symbol Z, you don't need to know this, but it's what we use, stands for the atomic number, which is how many what the atom has, how many protons. The symbol A stands for mass number. You don't need to know that. But the mass number is how many nucleons it has. That is how many protons plus neutrons it has. And again, I hope I'm skipping things that are okay to skip. I'll just, again, keep just going over the ones I circled. A nitrogen atom has 7 protons and 7 neutrons. If another, so these are isotope questions here. This is what I meant earlier about, here's some sample isotope questions I might ask. If another atom has 7 protons and 8 neutrons, is it still nitrogen? Yeah. 7 protons is what makes nitrogen nitrogen, right? So, but one has one more neutron than the other, so that means that they are isotopes of each other. Okay, 5 is kind of a question I could ask about isotopes, or 6. Which one of these could be the isotope of carbon-12? Well, it has to be carbon, so it can't be these two. Isotopes have to be the same elements, but it has to have a different number of neutrons, which gives it a different mass number. Remember, that's the protons plus neutrons. So it can't be that. That's the same atom. So it must be this. 6, an isotope of boron has 5 protons, 5 neutrons, and 5 electrons, which would be another isotope. Well, it has to have 5 protons. It has to be the same elements. So that cancels those two. So it's kind of like the previous question. But this one had 5 neutrons, so we need to find something that has a different number of neutrons, and that's A. All right, so I'll do a few of these, like number 7. Questions, I can't ask all these follow-ups, but I could put in one question like, here's this, how many protons, neutrons, and electrons it has, and I give you like multiple choice for all 3 of those answers. But I'm not going to ask you 7 questions and use 7 of my 100 points on asking this, but be able to answer all these. So there's magnesium-26. What is its atomic number? So, of course, I'm going to provide a periodic table for you, and I'm hoping you've memorized this. Yes, I made a mess of this periodic table, but there's magnesium. But remember, I had you memorize the periodic table by column, so I hope you remember that it was an alkaline earth metal. So again, I'll go up a little bit faster here. Its atomic number is 12. That's how many protons it has, which I'm going to ask you. It's actually down here. That's what the atomic number is. It's the atom in the periodic table, but that represents how many protons it has, the atomic number. The mass number is 26. That is its mass number. So that represents how many nucleons it has. But the nucleons include protons and neutrons. So if it has 26 nucleons, and 12 of those are protons, the other 14 must be neutrons. How many electrons would it have if it's neutral? It has to have the same number of protons and electrons. What is the approximate mass of one atom of this? It'll be about 26 Dalton. Give me an example of an isotope of magnesium, 26. For now, we'll just say choose any number you want, magnesium 27. All right, what do we got in the second column? Another problem like this, but now we have a charge. What is the atomic number of selenium? Well, you look in your periodic table. Do you remember what column it is? It's under oxygen. So it's 34. Actually, I should have known that, but I just wanted to check to be sure. So, oh, sorry, it was easier than that. This one, unlike the previous problem, I gave you the atomic number. I didn't need to look. So that's the atomic number. What is its mass number? 82. What is the approximate mass? 82 Daltons. Pretty easy. How many protons, neutrons, and electrons does it have? 34 protons. That's the atomic number. Neutrons is this minus that. It's the mass number minus the atomic number. So what is that? 48. And the number of electrons, notice it's charged minus 2. So if it has 34 protons, but it's charged minus 2, it must have 36 electrons. I hope that makes sense. 10. An atom has 15 protons, 17 neutrons, and 18 electrons. Which element is this? Well, who cares about the neutrons and electrons? It's the element that has 15 protons. So if you look in your periodic table, it's the one after silicon, which is phosphorus. Okay, go back to, so this is phosphorus. How many nucleons does it have? Well, that's protons plus neutrons, 32. What is its mass number? Well, 32. What's its approximate mass? 32 Daltons. Okay, so I'll skip those. But here are some isotope questions. Again, let's do really quickly. Oh, these are the puzzle problems. Good. This is what I meant. I'll probably put one of this type on the final. An isotope has 29 neutrons and a mass of 57 Daltons. Well, right there, how many protons does it have? Well, the mass is just going to be pretty much the combined number of protons plus neutrons. So where are the other 28 Daltons? It must be due to the protons. So even without even looking at the question, this must have 28 protons. But it has a charge of plus 2. How many electrons does it have? Well, if it has a charge of plus 2, it must have 26 electrons. Does that make sense? I had to find the number of protons from that information. So I have 28 protons. But if it's charged plus 2, it had to have only 26 electrons. Write the symbol for the atom in the previous problem. So you have to write symbol. Oh, no, you don't have to, but I could give you choices A through E and ask you which is the right symbol. So I need something that has a mass number, an atomic number of 28, but a mass number of 57, and it's charged 2 minus. And I'm not sure why I'm blanking right now. My brain isn't working. I thought that's copper, but I think it's the one before copper. Yeah, it's one before copper. Nickel. I know, it's embarrassing that I don't know that, right? So that is nickel. Okay. Let's do another puzzle. An isotope has, just writing the symbol. 29 protons, there's the atomic number. The number of nucleons, the mass number, is what? 62. And it has 28 electrons. So if it has 29 protons and 28 electrons, the charge is plus 1. Now that is my copper. Okay. All right, so let's keep going. I don't do as many down here, and plus I'll tell you to skip some. So maybe just to go over some terminology here, just in case it comes up. For that thing here, the 26 is known as the atomic number, which is how many protons it has. 58 is known as the mass number, which is how many nucleons it has. The symbol for another isotope of iron would differ only in its mass number, the superscript, since it has a different number of neutrons, but the same number of protons. Okay, I don't know if I needed to go over that. That's okay. So let's do at least one more of these. Maybe, I think I circled another one later, but I don't think I need to do another one after I do number 4. What's the atomic number of that? And again, shame on me for not remembering this. But cobalt, let's find it. Sorry, I'm so zoomed in. is right here. So it's 27. I should know that, but I don't. Okay, so, oh, it's down here. There we go. So the atomic number is 27, so I'll even write that right here. What is its mass number? 58. How many protons? 27. How many nucleons? 58. Hope you're getting this. How many neutrons? It must be 58 minus 27, or 31. Its approximate mass is the number of nucleons it has. Electrons, well, notice it has 27 protons, but the charge is plus 3. So it must only have 24 electrons. Now, since it's a positive ion, it's a cation. And an isotope would be, still has to be cobalt, but a different mass number. I'll say cobalt 60, and it doesn't matter what the charge is. Okay. We'll do one more of these puzzle ones like number 7, and then I'll skip any that come later because I think you get the idea of what I'm talking about. An ion of a certain atom has a mass of 72 daltons. It has 28 electrons and an electric charge of plus 4. How many neutrons does it have? So if it has 20 electrons and an electric charge of plus 4, how many protons must it have? Must have 32 protons, right? But if it has 32 protons, but the mass is 72, how many neutrons must it have? Well, if the mass is due to the number of protons and neutrons, there must be 40 neutrons. Okay, I hope that makes sense. I hope I'm not making mistakes on these as I'm quickly trying to go over these. Here's what I was talking about before. I'm not going to ask you a question where you're calculating the average atomic mass, but I could. I'm not saying I'm not that I am, but I could ask you something like number 8, and I think I'll do another one later. So let's say that gallium has 2 naturally occurring isotopes, 69 and 71, and you look in the periodic table and notice that the mass is closer to gallium 69 than 71. So do you think that's just going to be which isotope is more abundant? Well, it must be 69 gallium because the average is closer to it. I'm probably not going to waste a question on that. Now, here's the other thing I said I might not ask, but do write down, if you can't remember, Kelvin is just degrees Celsius plus 273, and you can solve these. So what's Kelvin? What's 100 degrees Celsius in Kelvin? Add 273, and we get 373 Kelvin. So that's what I mean. They're always different by 273, and the Kelvin number is bigger. Well, here's 600 Kelvin. We'd want to subtract 273 to get the temperature in Celsius, and that's going to be 327 degrees Celsius. Yeah, again, I don't think I'm going to ask that, but we could. Same thing with 15, but it's nice for you to know that the temperature is a measure of the average kinetic energy, Ke, of the particles, so whether they're vibrating or moving around. All right, let's move on to 52. I covered this, so I won't go back up the periodic table, but know which of those things are metals or nonmetals or metalloids based on their position. But do know something like number 2. If an element is a solid, it's dull and brittle, and it's a good insulator, not a conductor. That sounds like what? A nonmetal. So know that. Use your periodic table to answer the following. I can't really go between back and forth, but let's see if I can just get the answers here. Which is the only element in group 1 that is a nonmetal? Well, that's hydrogen. Which element adjacent to the zigzag line is definitely considered a metal rather than a metalloid? If I went up there, you would see an aluminum. What is the name of the alkali metal in the 6th period? Okay, we'll go up there. So alkali metal is the first column, and the periods are the rows. So 1, 2, 3, 4, 5, 6. It's cesium. Okay, that's why I didn't want to go all the way up. We have to go find it where we left off, which is down here somewhere. Here we go. So that was cesium. I'm not going to waste time with D, but the 5th period, you're just looking for an element that starts with T in the 5th period, which is the 5th row. Which is the least massive halogen? Halogen is, you know what column that is, group 17. Just look for the one at the top, that's fluorine. What is the heaviest alkali metal? That's just going to be the bottom one in the first column. What's the physical state? Well, based on my key on that, you'd look for whether it's a solid or, what else did I do? I think I did italics for liquids, I think, and gases. I think I did like a asterisk, but yeah, I'm not going to ask that. Which element in the 4th period might you guess has similar properties to that of magnesium? Well, I'll waste time going there. So magnesium is an alkaline earth metal. And so fourth period is here. And so, right here. And so it'd be calcium because, again, elements in the same column tend to have similar properties. Again, I'm not sure if I'm going to waste time asking that on a final, not time, but waste questions I could ask. Berkeley and California, yay, Berkeley, California, are two examples of which series of elements? Those are the actinides. Okay, 4, write these down on your cheat sheet if you can't remember. Cesium, if we went up to the periodic table, that's an alkali metal, so those form +1. Oxygen, -2. Bromine, a halogen, -1. Magnesium, an alkaline earth metal, +2. Aluminum, group 13, +3. So write those down. If you look in the periodic table, number 9, at magnesium, it says 24.3. And let's say these are the 3 naturally occurring isotopes of magnesium. Which one do you think is the one that's found in the highest natural abundance? Well, the average is closer to 24. So I probably won't ask that, but I hope you get it. So here are some questions about differences between solids, liquids, and gases. So let's kind of go over these really quickly and get the answers. Which 2 states have their particles crammed together with no space between them? Solids and liquids. Which has them far apart? Gases, under normal pressure. Which state has particles organized neatly? Solid. 2 states that they're disorganized? Liquids and gases. Stuck in place but vibrate? Solid. Have the ability to move around, although with some limitations? Liquid. Complete freedom? Gas. Which states are compressible? Those are the ones that have a lot of space, or that's the one that has a lot of space between the atoms? Gas. Incompressible? Their atoms are already stuck against each other. Can take the shape of their container because they have freedom of movement. They spread out to fill their container. That would be gas and, just gas to completely fill their container, not just the bottom. What do you call the following changes of state? Maybe I'll say them verbally. Solid into a liquid is melting. Liquid to a gas, that's condensation. I'm sorry, I was looking at my time here. Liquid to a gas, that is boiling, or you could say evaporation or vaporization. A gas into a liquid, that's condensation. A liquid into a solid, that's freezing, we'll call it. A solid directly into a gas, that is sublimation. Don't forget that one. And the opposite, a gas to a solid, deposition. Okay. 53, I think we're going to get to radioactivity soon. I'll go ahead and skip 1. Feel free to look at the questions, but again, it's just identifying parts of the periodic table. Same thing with number 2. I know I circled it, but just go look at the answer key and you can go over it. I just want to kind of make this a little bit shorter because there are other things I want to spend time on. So here's like where you want to convert between grams. I'm confused because there's someone in the other room. I'm trying to listen to what they're doing. I think it's Zachary trying to do something. If you have 3 moles of boron atoms, how many is that actually? So again, I could show you a conversion factor, but let's do it logically. We know that 1 mole is equal to 6.02 times 10 to the 23rd. So all we're doing for these problems is either multiplying what we're given by that number or dividing. So understanding logically that 1 mole is that number, and I have 3 moles, what am I going to do with those 2 numbers? I'm going to multiply. So I don't want to take my time getting out my calculator and finding this. Actually, I can show. In fact, maybe I'll just do that down here. I'll show you the answer key. There we go. But in number 12 is the same idea. I have 4.5 moles. How many is that? Well, if each mole is this number, if I have 4.5 moles, it's just 4.5 times that number, right? But 13 is the opposite. I'm giving you the actual number, and I want to know how many moles that is. So for those, you're going to divide. And if you don't remember, write that down on your cheat sheet. Say, if I'm given moles and I want actual number, multiply by 6.02 times 10 to the 23rd. If I'm given the actual number and I want moles, divide by 6.02 times 10 to the 23rd. You see what I mean? There's no excuse not to get it. Because you can write that on your cheat sheet. But do know how to do those problems, because I'm not positive, but I might have space to do that. More likely, for sure, I'm going to ask you to convert between grams and moles, but I could, if I have space, ask you to convert between a number and moles. Okay, let's get to 54. I'll skip those again. Look at your answer key. I'm trying to save a little time on this. It's pretty much what I went over like 3 minutes ago, but look at the answer key. Same thing, even though I circled it, make sure you know that stuff. So maybe we'll go over it really quickly as a little review. What's the common name of group 1 metals, the alkali metals? Group 2, alkaline earth, 17 halogens, 18 noble gases. Which type of element tends to be solids and good conductors? Those are the metals. The nonmetals form negative ions, anions. Then we have the main group elements. I'm sorry, those are the transition elements. So what are the 1 to 2 and 13 through 18? Those are the main group elements. And then the period 3 means the third row. And so the bottom very 2 rows are lanthanides and actinides. Sorry, I'm still being distracted because I hear people in the prep room downstairs on the other side of my wall. I'm saying, I hope they're not doing anything bad back there. All right. So here's that idea I talked about earlier about the specialty of that number. What does it allow us to do? It allows us to say this, which is number 10. If I looked in the periodic table under magnesium, it would say 24.3. So that means that one single atom of magnesium, on average, of course, has a mass of 24.3 daltons. That's what the 24.3. One single atom has a mass of 24.3 daltons. A dalton is an incredibly small amount of mass. But if I have a whole mole of magnesium, meaning this many magnesium atoms, it would still be 24.3, but now it's in grams. It's something that you can feel in your hand. And then molar mass is just what is the mass per mole. And so I'm pretty sure it's 65.4, but let's see. What did I just say it was? I forgot what it was. But I'm just going to look and I'll pretend like I knew. So was I saying that, what was the molar mass of, I have no idea what I just said, what we're going to do, but I'll just pretend like it was zinc. And so you see 65.4. One atom of zinc would be 65.4 daltons. 1 mole of atoms of zinc would be 65.4 grams. So what we say is it would have a molar mass of 65.4 grams per mole. And that's how you'd write the units. Now I got to find out where I left off. I think it's this next one here. Yeah, it was. So I'd say it's 65.4 grams per mole. Okay. I probably won't ask 13, but yeah, which can feel the strong force? Protons and neutrons. And then terminology, I said I'd go over this. Probably not going to ask you any particular question about this, but just to be aware of the terminology. So if I have a problem that mentioned these, you know what it means. We'll pick up in that sentence here. A nucleus that can live indefinitely is said to be stable. But some nuclei, not having the right ratio of protons to neutrons, are going to be unstable. They will, well, I don't want to give away an answer later, but yeah, well, so they're unstable. So it's going to change in some way. And the way it changes is it shoots out some kind of particle, some kind of energy, and it undergoes a process of radioactive decay. I'm reading the sentence to see if I'm using the right term there. And we say that the unstable nucleus is radioactive. But here's kind of the big difference, not difference, but the difference between these two terms is the particle that it's shooting out when it undergoes radioactive decay. That's called the radiation. So the radiation is the particle it shoots out. Okay. Exclamation points. Yes, I will ask one question about this. So doing a little mini lesson here, the neutrons are kind of stabilize the atom because the neutrons contribute to the strong force to keep the nucleus together, but they don't introduce any new electric repulsion. So we got 3 regions of the periodic table, and rule of thumb, not exactly, there's a certain number of neutrons it needs compared to protons to have a chance of being stable. So I said that from elements of like from Z from 1 to 20-ish, just a rule of thumb, you want about a number of neutrons around the same as the number of protons. And that would give it a good chance of being stable. Not guarantee it, but that's what we're looking for. But when you get to element 21, not really right then, but around this region, around 20 to 21, up to element 82, which is lead, you want your number of neutrons to be greater than the number of protons. And in fact, you need an increasingly greater number of neutrons compared to protons as you head towards the heavier elements. So by the time you get to like element 75, 80 or whatever, you need almost 1.5 neutrons compared to protons. So if we're at element 80, which is mercury, we just don't want, let's say, 81 neutrons, which would give it a mass number of 161. We'd probably need like 115, 120 neutrons. So the mass would be like 200 or something like that. So I'm not going to get that technical on it. Now, the easy one is elements 83 and above. Those are all unstable. It's just automatically unstable. There's no number of neutrons that will make it stable. So write that down in your note sheet so you can answer these. So let's go ahead and do this. There's another one later, I think, besides 17 and 18. For elements 1 through, I think it's just repeating what I just said, so let's do it really quickly. For elements 1 through 20-ish, how many neutrons are needed? About the same number of neutrons as protons. 20-ish, oh, I made a mistake there, sorry. I should say 20 calcium. And again, I know before I just said 21, but there's no hard line. I'm just saying, after we get to 20, we start to need more neutrons than protons. And for those greater than lead, none will be stable. So let's go ahead and do a real problem. So if I gave you just zircon 80, I'm probably not going to do that. I'm going to make you work a little harder on the final. So you would need to look in the periodic table if I gave you, I don't know why I just said zircon again. I'm just kind of frantic here, trying to talk fast. Zirconium 80. You would need to look in the periodic table and you would find out that that's element 40. So it means it has 40 protons. But that 80 does not mean it has 80 neutrons. Remember, you need to subtract. So if it has 40 protons according to the periodic table and the mass number is 80, it must have 40 neutrons. So is that likely to be stable or more likely to be unstable? Well, we're in this kind of second region here, right? So we need more neutrons than protons, and not probably just one or two more. So I'm pretty darn sure that's going to be unstable. We're in that second region that we definitely need more neutrons than protons. Now, what if I said 81? So it had 41 neutrons. I'm still going to say it's almost for sure unstable because by the time we get to element 40, we just don't need one more neutron. We might need 5 more neutrons or something. All right, what about thorium-230? So again, if I didn't give you this information here, you'd have to look in the periodic table and see where thorium is, and you'd find out it's element 90, so it has 90 protons. And so when you subtract it from 230, you find out it has 140 neutrons. Now don't get fooled, don't say, oh, it has more neutrons and maybe 1.5 times more. No, I don't care. It's above element 82, it guarantees it's unstable. All right, this one, again, you look in the periodic table and see it's element 7, so it has 7 protons and therefore 7 neutrons. Yeah, that seems right. That for those lighter elements, we want about the same number of neutrons as protons. Okay, I know this is getting pretty long, but let's keep going. Let's get to, I think we go up to 58. So let's take a look at start doing radioactivity. I've already covered this. If it has too many neutrons, let's say, it won't exist. We say the atom or the nucleus is unstable, meaning it will undergo radioactive decay and it emits particles we call radiation. Okay, which of these are likely to be stable or unstable? Let's do that one more practice for this, and if I have any later, I'm going to skip it. So we're talking about aluminum, and I gave this to you, but know how to find it in the periodic table. So this has 13 protons, and how many neutrons? 14 neutrons. I'm going to guess that's stable, because I know it's not exactly the same, but they're about the same. So I'm going to make a guess that that's stable. What about mercury 200? Well, you would look up, if I didn't give this to you, and see that it has 80 protons. And how many neutrons does it have? 120. That's about 1.5 times more neutrons than protons. That's pretty good for something so heavy. So I'm going to guess that that's stable. But now for fermium, I gave it to you, but you can look up in the periodic table. It has 100 protons. Immediately, what do you know the answer is? It's unstable. Boron is element 5, so this has 5 protons and 5 neutrons. Yeah, same number. We'll say it's stable. And lead 172, that has 82 protons. It could be stable, but that has 82 protons and 90 neutrons. I know that's more neutrons than protons, but we're there at those really heavy elements. By that time, we need about 1.5 times as many neutrons as protons to have a chance of being stable. So I'm pretty darn sure that's going to be unstable. Okay, in alpha decay, what gets shot out, the radiation that it's being shot out, we call it an alpha particle, but what really is a helium-4 nucleus. Okay, Zachary's really scaring me. He's like screaming in the other room. Zachary, if you're listening to this, please don't be up to any no good in there. But I want to pause. I just want to finish this show and just have one long document here. But let's do this. I'm not going to go through this. Read the things here if you need to be led through it. But the more likely thing I'm going to ask is, what goes in those blanks, and give you multiple choice or something. You should know this. Or I can do some kind of subset of a question. So alpha decay, if you had to balance this, know that one of the two products is the alpha particle, the helium-4 nucleus. And write the 2 and write the 4. Again, write this down on your cheat sheet. There's no reason to miss problems like I'm about to go over. They're just variations of the same problem. I'll just vary what that is. Or there could be a problem where I give you that and ask you for the parent. Remember, the original is called the parent that's decaying, and the thing it turns into is called the daughter. So if you do that, all you have to do is balance the superscripts and subscripts. So this has an 88, for alpha decay, and this has a 2. So what goes there? An 86. That's 224, and the top is 4. So what goes up there? 220. And then to find what element that is, you just look in the periodic table for element 86, and yay, I think I know one, radon. Okay, simple as that. Be able to do it. All right, let's try this one. And I told you it's alpha decay. We kind of, well, I guess I shouldn't say we know, but so do this. If I give you this and say, fill in all the blanks or some kind of multiple choice, it doesn't have to be the second one, but I'll put it second. There's my alpha particle, the helium nucleus. So let's balance the superscripts and subscripts. This is going to be 92, right? And that's going to be 232. And you look up element 92, and that's uranium. Okay, so that's alpha decay. Now another type of decay is beta minus. So it emits 2 particles. And I could just ask a question like this. What's emitted in beta minus? It's going to be an electron and an antineutrino, which we symbolize as E minus, and this, the thing with the bar over it. Okay, and we'll do it one a little bit below at number 12. In number 11, in beta minus decay, what turns into what, ignoring the antineutrino? Well, a neutron is turning into a proton plus the electron plus the antineutrino, right? So let's just go ahead and balance one. So here's something that's beta minus. Feel free to pause and read that if you need to be led through it. But it's going to, I could ask you something simple like that, but maybe more likely I'm going to give you something like this, that you're going to do multiple choice and tell me what goes into some of those blanks. But I could ask you something like that, so kind of understand the thought process behind this. So I'm going to give you a hint how you could solve this also, but first I'm going to do it based on what I said here. So notice that what I have there is something that has 20 protons, and how many neutrons? Well, if it has 48 nucleons, it has 28 neutrons, right? So in beta minus decay, a neutron turns into a proton, and we won't worry about the electron. Well, in fact, we'll write the electron here. So beta minus, we know one of the products is an electron, which we just set up here, and the other is the antineutrino. But to get the blanks there, remember that this has 20 protons, but in beta minus, one of the neutrons, so I should highlight that one, turns into a proton. So if I had 20 protons to begin with, and a neutron is turning into a proton, how many protons will I have at the end? 21. But we just lost a neutron, so now we only have 27 neutrons. Sorry, I didn't mean to write that. We only have 27 neutrons, but if we have 27 neutrons and 21 protons, we still have 48 nucleons. So notice that the mass number did not change. We didn't lose any nucleons, it's just one of them turned into the different type. So we still have 48 total nucleons, it's just one of the neutrons turned into a proton. So what is element 21? You look it up, and I believe that's scandium. If I'm wrong, excuse me. So notice a couple of things here. In beta minus decay, what's happening is it's turning into the next element in the periodic table. But the mass number stays the same, if you can read my handwriting there, okay? So that might be a question I'm gonna ask you a little bit later as we do some more problems. But write that down. In beta minus, you end up with the next element in the periodic table, but the mass number stays the same, and you're emitting an electron and an antineutrino. Okay, we'll do more of these in a second, but here's that thing where I'm gonna ask you one question, how to convert from grams to moles or vice versa. So what you do, and I want you to use a conversion factor to make sure you think about this, is let's say how many moles are in 50 grams of neon? Well, let's take what's given to us, 50 grams. And remember, that's like 50 grams over 1. What we do for our conversion factor is use the molar mass of neon. So I know what it is actually, but I'm going to remind you which one it is when you look at the periodic table. It's not the top number, it's the bottom number. So there is the molar mass of neon. Yes, and I did know what it was. That's one that I do know. So now here's the problem, I have to find it. So it's 20.2 grams per mole. I'll write it here. That is the molar mass of neon. So always on your conversion factor, you're gonna write the mass, for example, 20.2 grams on one side of the conversion factor, and the other side, you're always writing 1 mole. So for this one, I'm trying to get rid of grams. So what am I gonna write on the bottom? I'm gonna write the 20.2 grams. That way, the grams could cancel. And what I'm writing at the top is 1 mole. After all, I want to find moles, right? So you're gonna take 50 and divide by 20.2, and you're getting like 2.5, right? We'll look at the answer below on the answer key. Meanwhile, let's do this one. 0.4 moles of gallium. What is its molar mass? Oh gosh, am I gonna have, I'm gonna lie to you. Well, we'll look at the bottom. We'll go ahead and look at the bottom because I don't wanna scan back up. But again, what we would do is, this is the opposite. I have that many moles, so we're gonna put 1 mole on the bottom and put whatever number of grams gallium is at the top, and that way moles can cancel. And we're left with some number of grams. So please write down a sample problem of each, including kind of writing how it's worded. So when, not if, when I give you a problem to convert between moles and grams and moles, you just follow your little sheet and you know exactly what to do. So again, I told you I'd show you this. There it is. It's 69.7. There was no way I would remember that. But again, notice how all I'm doing to convert between grams and moles or moles to gram is just using the molar mass of that chemical. But if I'm trying to cancel moles, I put moles on the bottom. If I'm trying to cancel grams, I'm putting grams on the bottom. Okay, we're getting close to the end, so my voice might hold off. I'm sorry it kind of went so fast. I maybe shouldn't have gone over the little review at the beginning and just started doing problems. So let's do another one of these. This is kind of finding the mystery thing, and it's undergoes alpha decay. So here's how you do it, pretty easy. What is the product of alpha decay, or the radiation of alpha decay? It's the helium-4 nucleus. So how do we get the parents? Conserve, if you want to use that term, the superscripts and subscripts. So this must be 101, and this must be 256. And then you look up what element 101 is, and that's Mendelevium. The other product is the alpha particle. Is the alpha particle radioactive? No, it's just stuff like you breathe in a balloon. That's just helium-4, that's normal helium. But it's the radiation, and what's dangerous about it is not that it's helium, it's just that it's being shot out at a high speed, and like little bullets can run into your skin. Here's a kind of problem I could ask. Again, I don't have a lot of space to ask a bunch of radioactivity questions. Without writing the entire equation like in the previous problem, simply write the symbol for the daughter if this is going alpha decay. So remember, in alpha decay, it's losing 2 protons plus 2 neutrons. No, I didn't say that wrong. It loses 2 neutrons, but it's losing 4 nucleons altogether. So all I need to do is take away 2 from the number of protons, but then take away 4 from the number of nucleons. And then I just look in the periodic table, and element 82 is lead. So you should be able to do something like that without having to do this whole thing here. That's the daughter. For alpha decay, it loses 2 for the bottom number. It loses 4 for the top number. I'll kind of skip this. You can look at the answer key. I think it's just kind of, well, maybe since it brings up beta plus and gamma, I'll go ahead and do it. In alpha decay, the radioactive nucleus emits an alpha particle, which is actually a helium-4 nucleus. Since the parents, okay, let's say you start with element 87. If it alpha decays, what element is its daughter? 85. It loses 2 protons. In beta minus decay, the nucleus shoots out a newly created electron and an antineutrino when a neutron turns into a proton. You might even want to write that down. Like maybe I could ask a multiple choice question that says, in beta minus, what is turning into what, like I did on the previous homework sheet. So make sure you know that. Write that down. Say you start with element 87 again. If it beta minus decays, what element is the daughter? So that's what I mentioned about 2 minutes ago. Know that in beta minus decay, you end up with the next element in the periodic table. So we're going to go up to element 88. In beta plus, it's just the opposite. The nucleus shoots out a newly created, even though I haven't introduced this term before, not before, but today, a positron. That's just a positive version of an electron, plus a neutrino when the proton turns into a neutron. So because a proton is turning into a neutron, we're losing a proton, it's turning into the previous element in the periodic table. So if something beta plus decays, well, element 87 beta plus decays, we're going to end up with a daughter, which is element 86. So write that down, or these things down. Beta plus, a proton is turning into a neutron plus an electron plus, a proton is turning into a neutron plus a positron plus a neutrino, but also write down that in beta plus, you end up with the previous elements. Now in gamma decay, the nucleus shoots out a newly created, you can say gamma ray or photon or something, but that's what it's shooting out. But it's not changing the number of protons or neutrons, so the daughter is the same. It's still element 87. Okay, I could ask a multiple choice, but again, I don't have tons of questions. I got 50 questions I could ask on the whole semester of chemistry. 4, here we go with beta minus. So I know immediately beta minus is an electron plus the antineutrino. And I said I was going to do a shortcut a little bit later, and I'll do it for this problem. I didn't do it before. But again, what happens in beta minus? What element do we end up with? Which is kind of, I guess, a shortcut in itself here, rather than the original way I did it, of like thinking of the number of protons and neutrons. In beta minus, you end up with the next element. So we're going to be at element 92. That's what happens in beta minus. You end up with the next element. And then you look up and see that's uranium. And then the mass number does not change. Write that down. It's still 234. Now, maybe I feel guilty about introducing this. Actually, I won't. I was going to do something about often you can write little numbers here and balance superscripts and subscripts, but I don't want to confuse you because I never brought that up before. Just do the method where you know that in beta minus, you end up with the next elements. Let's do another one, beta plus, actually. So beta plus, we form the positive version of the electron called a positron, and we produce just a regular old neutrino, not the antiparticle of the neutrino. The positron is the antiparticle of the electron. So as I said, you could think about it kind of logically, but in beta plus, you end up with which element as your daughter? The previous element. So we're going to end up with element 5, which is boron, but again, the mass number does not change. So with beta minus and beta plus, the mass number does not change. Write those things down in your cheat sheet, or you can write down sample equations and kind of follow it along with whatever else I give you to do that. Okay, gamma decay is really easy. It doesn't really change anything. It's just relaxing, getting rid of energy. So that's just a symbol to mean a photon. It's specifically a really high energy photon, a gamma ray. I'm going to skip this. I'll let you try that one on yourself. But again, I'll have probably one question on which of these are likely to be stable or something. So look at the answer key for that. I'm just kind of moving on here. Really quickly, it doesn't take long. We're almost done. What is the radiation alpha particle? It's that. Beta plus, that. Beta minus, that. Okay, I don't think that was worth it, I guess. And again, this is a skill which I can't ask that many questions on the final, but I could just ask them this way. So identifying what type of decay happened if that's the parent and that's the daughter. Again, write this down. If something is doing beta plus decay, it goes down to the previous element. And that's what happened here. We went from 47 to 46. That's telling me it did beta plus. This went up in elements. So the daughter has one more proton. That's telling me that it's beta minus. This one didn't change, so that's telling me it's the gamma decay. But this one went down by 2, so what does that tell you? It's alpha. So that could be a nice quick question I could ask. I can do something like that. I'm not saying I am, but it's just something that might lend itself to a multiple choice question, because I just have choices A, B, C, and D, or whatever. Just identifying what type of decay. These are pretty quick, so I'll go ahead and do them. So again, let's practice this. Positron decay, beta plus decay, we end up with the previous elements, but the mass number stays the same. Gamma decay, nothing changes. It's just the nucleus is getting rid of energy. This is beta minus, right? So we end up with the next elements in the periodic table, and oh no, but the mass number changed the same. Again, I haven't practiced this in a while, but I'm pretty sure that's actinium. Then notice this is an alpha particle, but we can do the balancing the superscripts and subscripts technique. So this must be 102, which is nobelium, and then it's losing 4, so 257. This is trickier, so there's a lot of things to fill in, but do I tell you what type of decay it is? Oh, I could. So you need to look up to see what element number mercury is. And when you do, you find out it's element 80. That's the first step. So notice we went to the next element in the periodic table. So what kind of decay is that? That's beta minus. So now we can fill in those. And remember, in beta minus or beta plus decay, the mass number doesn't change. And so now you need to look at what element that is. And I want to say that's gold, but if I'm wrong, I'll look down below. I'm wrong. Let's try this one. Recall that beta minus decay is when a neutron turns into a proton, and beta plus is when a proton turns into a neutron. If you have an element of neon 25, which one do you think will occur? Well, that has 10 protons and 15 neutrons. Probably unstable, because that has way too many neutrons, right? For such a light element, it should have about the same number. So this will want to do something that will get rid of a neutron, right? So what kind of decay, beta minus or beta plus, turns a neutron into a proton? So it would get rid of a neutron and make a proton. In other words, it would make something that has only 14 neutrons and 11 protons. Well, the type of decay that turns a neutron to a proton is beta minus decay. All right. Now, I know I said we're almost done, but I'm going to go ahead and do these one more time. So how do you convert? Write down sample problems. I'm going to ask you something like this. To convert between grams and moles, you look up the molar mass of that. And so iron is 55.8 grams per mole. So on one side, we're going to write 1 mole. On the other side, we're going to write 55.8 grams. But since we're trying to cancel grams, I'm going to put 55.8 grams on the bottom and 1 mole on the top, so the grams cancel. Meanwhile, sulfur, which is 32.1 grams per mole, I need to cancel moles, so I'm going to put 1 mole on the bottom so they cancel, because that's like 6.5 over 1, and 32.1 grams on the top. So be ready for that. All right, I was right. So that's gold. And I was wrong about that. Sorry, francium. What is actinium? Actinium, I guess that's 89, I guess. Okay, sorry about that. And then, yeah, there are the actual numbers that you can look on the answer key. And I skipped some other things. Again, go over the problems and do those. All right. I'll go ahead and skip these. I think you guys get the idea. But let's do half-life. I think that's the last thing, and we'll call it a day. Hopefully this is under an hour and a half. Write this table down if you didn't hear me, unless you're absolutely confident you can figure it out. Okay? So let's try some of these with use of that table. I'm going to not zoom in just so we can see the table if you need it as I'm reading the problems. You have an unstable nucleus, number 6, sitting there. It has a half-life of 20 minutes. After 20 minutes, what are the chances it decay? Oh, this is just kind of a basic thing, 50%. We'll skip this one. No, actually, the second part is relevant. Now you have 1,000 of these nuclei after, no, that's still the same thing. Just kind of the definition of half-life. So let's do one that's actually a little bit more interesting. Number 7. The half-life of a particular radioactive isotope is 2 hours. So I can zoom in a little bit. You wait 6 hours. How many half-lives have passed? Three half-lives, right? So 3 T1 halves. So well, I'll go ahead and read the question. I was going to say something. You know that how many half-lives have passed? What fraction of the original sample remains? Well, look at our table. After 3 half-lives, 1/8 remains. So if we had, I'll just ask for the fraction. So we'll have 1/8 remaining. Okay. Now, if you try to make this table on the fly, here's what the mistake people make. They go like this. They go 0, 1, 2, 3, or whatever. And in the second column, they say, okay, this is going to be half, 1/4, 1/8, or whatever. No, after 0, the whole fraction is remaining. So it's only after the first half-life that we have a half. So that's why I said copy down the table if you're prone to make that mistake. All right, number 8, I'm trying to hurry because I know this is long and they're still creating havoc in the prep room. So I got to go in there and check to see what they're doing. You have a sample of a radioactive isotope. After a certain amount of time, you notice you only have 1/4 left. Well, 1/4 left means how many half-lives have passed? Well, 2 half-lives, and that's just what the question's asking. But hopefully we'll get to slightly trickier problems here. You start with 16,000 radioactive nuclei. If you wait 4 half-lives, about how many should you have left over? Well, 4 half-lives, we should have 1/16. And so I said, don't just give me 1/16. How many is that? That's going to be 1,000, right? You start with 640. Oops, didn't mean to do that. Sometime later, you have only 20 left over. Well, what fraction is that? We have 1/32 left over. So how many half-lives must have passed? About 5, right? Sorry, I'm going fast, but I hope you get this. The half-life of isotope is 5 minutes. So I'm probably more likely going to ask you something a little more challenging like 10 or 11 or something. The half-life is 5 minutes. You start with 32,000. You wait 15 minutes. How many atoms should be left over? Again, feel free to pause if you want to think about this. So let's look at this information. That tells us 3 half-lives have passed. So that tells me what fraction is remaining. I should have 1/8 remaining, right? And if 1/8 remains, I should have 4,000 left over. Okay. I think I did that. And then 59, I didn't circle any, so maybe we're good. They're just more practice problems, I think. So that's it. I know I went a little bit fast, sorry about that, but this is not particularly challenging material. Just make sure you go back and practice all that and write all those things down I said. Okay, thanks for listening, bye.